Something is moving through the darkness between worlds, and it's doing something it shouldn't be able to do. An object from another star system, designated 3I/Atlas, has begun exhibiting behavior that challenges our understanding of how natural bodies move through space. Multiple independent observations report a subtle but persistent acceleration, a gentle push that gravity alone cannot explain. The trajectory calculations suggest that if this acceleration continues for just 50 days, the velocity change could be enough to alter the object's path significantly. Some claim it could line up with Earth. Others suggest we're witnessing the first confirmed instance of an interstellar probe executing course corrections as it approaches our world. This isn't science fiction dressed up as astronomy. The object exists.
It was discovered through systematic sky surveys designed to protect Earth from potential impactors. Its trajectory has been calculated with precision by some of the world's most sophisticated orbital mechanics teams. The non-gravitational acceleration has been measured and documented by multiple independent facilities using different instrumentation and analysis methodologies. What remains uncertain is what that acceleration means and where it will lead. Are we observing an unusual comet behaving in ways our models don't adequately capture? Or are we watching something fundamentally different? Something that demands we reconsider assumptions we've held about our cosmic isolation? The significance of this question cannot be overstated. Throughout recorded history, humanity has wondered whether we're alone in the universe. We've crafted myths and religions, attempting to address that uncertainty.
We've searched the skies for signs of other intelligence. We've pointed radio telescopes toward the heavens, listening for voices across the light years. Yet despite centuries of scientific observation and decades of deliberate searching, no confirmed contact has occurred. We remain isolated, at least as far as definitive evidence suggests. If 3I Atlas represents something more than a natural comet, if it truly exhibits characteristics suggesting artificial technology or intelligent control, the implications would rewrite everything we think we understand about our place in the cosmos. The debate surrounding 3I Atlas represents more than just one object's peculiar behavior.
It embodies the tension between scientific caution and imaginative possibility,
Between explaining observations through established physics and remaining open to revolutionary implications. Throughout history, anomalies that initially seemed inexplicable eventually found explanations within expanded theoretical frameworks. Sometimes those frameworks required modest adjustments to existing models. Other times, they demanded complete reconception of how nature operates at fundamental levels. We don't yet know which category this visitor falls into, but the investigation proceeding right now will provide answers over the coming months. What makes this situation particularly compelling is the convergence of multiple unusual characteristics.
The object arrived from interstellar space on a hyperbolic trajectory,
Meaning it's not bound to our sun and will eventually depart back into the galactic void. Its closest approach to the sun occurred near the end of October, placing it in the inner solar system where solar heating should trigger substantial outgassing if it's composed primarily of ices like typical comets. Yet the visible signatures of massive gas and dust release haven't been definitively observed at the levels the acceleration calculations suggest should be present. The object's color measurements indicate something unusual about its composition or surface properties. Reports describe it as bluer than the sun itself, suggesting ionized gases or materials we don't typically associate with cometary bodies. The acceleration itself is tiny, approximately 0.02 of a millimeter per second squared.
That's about 1/50,000th of the gravitational acceleration we experience on Earth's surface.
Standing still, you don't feel it. Walking, you wouldn't notice it. But in the vacuum of space, over days and weeks, such persistent forces accumulate. They change velocities by meters per second, then tens of meters per second. They shift trajectories by hundreds of thousands of kilometers. What seems negligible becomes significant when integrated over time and distance. The question isn't whether the acceleration exists. Multiple independent observation teams have confirmed it. The question is what physical mechanism produces it. and whether that mechanism is natural or represents something more exotic. Calculating the consequences of sustained acceleration requires only basic physics, principles taught in high schools and universities worldwide.
Acceleration multiplied by time equals velocity change. If the acceleration continues unabated for 50 days, the cumulative velocity change approaches 90 meters per second. In orbital mechanics, such changes can significantly alter where an object crosses a particular plane or when it reaches a specific point in space. The claim that captured attention suggested this velocity change, applied in precisely the right direction at precisely the right time, could convert what's currently predicted as a distant flyby into something approaching an Earth intercept scenario. That claim requires multiple assumptions to hold simultaneously: that the acceleration persists for the full duration, that its direction happens to point toward Earth's future position, and that the timing aligns perfectly with Earth's motion around the Sun.
Each of these assumptions is questionable when examined carefully. Cometary outgassing typically varies with distance from the Sun, strengthening near perihelion when solar heating peaks and weakening as the object moves away. Whether the acceleration measured near perihelion will persist for weeks remains uncertain. Cometary outgassing doesn't follow predictable temporal patterns independent of the object's distance and orientation. The direction of the acceleration matters as much as its magnitude. A sideways push might change the orbital plane without significantly altering the miss distance from Earth. A prograde thrust speeds the object up, changing arrival times. A retrograde thrust slows it down. A radial push toward or away from the Sun modifies the orbit's shape. Without knowing the acceleration's vector precisely, predicting its effect on Earth encounter geometry becomes speculative rather than deterministic. The timing component adds another layer of complexity to the analysis. Earth orbits the Sun at approximately 30 kilometers per second, covering vast distances in hours and days. For an object to intercept Earth requires not just reaching the right position, but doing so when Earth actually occupies that position. A trajectory shift that moves the crossing point by hundreds of thousands of kilometers might place the object closer to Earth's orbital path. But if Earth has already passed that point, or hasn't arrived yet, no encounter occurs. The geometric and temporal coordination required for an actual impact or extremely close approach is extraordinarily demanding. Natural processes producing acceleration through outgassing don't preferentially orient themselves toward Earth. They respond to solar heating, to rotation, to surface features that expose fresh volatiles. The alignment would need to be coincidental to an implausible degree. Official agencies responsible for tracking near-Earth objects have stated explicitly that 3I Atlas poses no threat. NASA, the European Space Agency, and other institutions with access to comprehensive orbital models have calculated the miss distance at approximately 1.8 astronomical units, roughly 270 million kilometers. That's more than 30 times the threshold used to classify objects as potentially hazardous. If the calculations suggested even a small probability of closer approach, planetary defense networks would have elevated the object's priority status immediately. The absence of alarm from professional communities suggests that when all factors are properly accounted for, including uncertainties and potential perturbations, the trajectory remains safely distant. Yet the anomaly persists in demanding explanation. If the acceleration isn't dramatically altering the Earth encounter geometry, it's still revealing something important about the object's nature. Comets experience non-gravitational forces routinely, as volatiles sublimate and jets of gas push against the nucleus in response to solar heating. Astronomers have modeled this phenomenon for decades across hundreds of documented comets. The calculations are well understood. What makes 3I Atlas noteworthy is the magnitude of acceleration relative to the object's estimated mass. If the mass estimates are correct, suggesting tens of billions of tons, then producing the observed acceleration through outgassing requires releasing enormous quantities of material. The momentum conservation equations are straightforward and have been verified countless times. The thrust force equals the rate at which mass is ejected, multiplied by the velocity of the outflowing gas.
When researchers applied these equations to 3I Atlas, they found that sustaining the observed acceleration would require losing approximately 1/6 of the object's total mass over roughly 30 days. That's not a modest adjustment to existing models. That's a comet evaporating a substantial fraction of itself in a remarkably short period. Such massive outgassing should produce unmistakable observational signatures visible across multiple wavelength regimes.
A huge cloud of gas and dust should envelop the nucleus, visible to telescopes as a glowing coma stretching across hundreds of thousands of kilometers. Spectroscopy should reveal abundant volatiles: water, carbon monoxide, carbon dioxide, organic compounds sublimating into space under solar heating. The tail should be prominent, pushed away from the sun by solar wind pressure and radiation pressure exerted by photons. The spectroscopic features should be distinct and identifiable. Thermal infrared observations should detect the heat generated by massive sublimation processes. Yet comprehensive observations matching these predictions haven't been definitively reported by multiple independent facilities. This discrepancy between predicted and observed outgassing has sparked considerable debate within the research community. Some astronomers suggest the observations simply haven't been conducted under optimal conditions. The object was behind solar glare at perihelion, making ground-based observations impossible from Earth's surface. Space-based coronagraphs, designed specifically to image the solar corona, can only capture objects very close to the solar disk, using carefully positioned occulting masks. The window for detailed observation of the object's coma structure and total outgassing rate was genuinely limited by these geometric and instrumental constraints. More comprehensive observations would require waiting until the object emerges fully from the solar conjunction zone, and those observations are now scheduled to occur around December 19th, when the object becomes accessible to all major observational facilities simultaneously. This explanation carries considerable weight. It's reasonable and accounts for instrumental limitations that are well documented. Space agencies and observatory directors worldwide understand coronagraph limitations intimately. Yet other researchers suggest something more fundamental might be operating beneath the surface of this debate. If the observed acceleration cannot be adequately explained through normal cometary outgassing according to standard theoretical models, what alternative mechanisms remain available within established physics? The options begin to narrow considerably when you eliminate conventional cometary physics as the primary driver. You could invoke exotic materials, or exotic processes we haven't adequately modeled in previous research. Ices with unusual thermal properties that sublimate differently than water ice or carbon dioxide ice. Minerals that respond to solar radiation in unexpected ways, not captured in existing spectroscopic databases. Electromagnetic interactions with solar wind plasma, or disturbances in the interplanetary magnetic field, could theoretically produce acceleration-like effects measurable by instruments precisely tracking the object's position and velocity over extended periods. All these explanations remain speculative, but scientifically plausible, without requiring anything beyond established physics and known chemical principles. They represent the kind of creative thinking that advances planetary science. Yet simultaneously, they also represent increasingly exotic extensions of standard models. The more unusual the material properties or processes invoked, the more carefully researchers must verify these explanations against multiple independent observations. That's how science progresses. Unusual claims require more evidence than ordinary ones. The threshold for acceptance rises with the extraordinariness of the explanation proposed. There exists, however, another category of explanation that some researchers increasingly discuss in private conversations, during coffee breaks at conferences, and in online forums dedicated to space exploration, though rarely in official scientific channels or formal peer-reviewed publications. What if the object possesses active systems capable of generating thrust independently? What if the acceleration represents not passive response to environmental conditions, but active propulsion,
executed by intelligent control systems.
Such systems would require multiple components working in coordination.
Energy sources to power the propulsion, mechanisms for conversion of that energy to kinetic thrust, guidance systems capable of calculating required trajectory adjustments, and control systems capable of implementing those adjustments with precision. These would represent technology far beyond human capability as of now, which is precisely why such suggestions are treated with considerable caution in mainstream scientific discourse. The burden of proof for such extraordinary claims must appropriately be very high indeed. Throughout history, people have proposed exotic explanations for astronomical phenomena without adequate evidence.
The patterns in astronomical data can appear to human minds to contain intentionality and design because our brains are wired, through evolution, to recognize patterns and to attribute agency to ambiguous phenomena. This pattern-seeking tendency served our ancestors well in survival context, but can mislead us when dealing with complex natural systems. The scientific method exists partly to counteract these cognitive biases by demanding rigorous evidence and independent verification. So mainstream science remains appropriately skeptical of proposals involving artificial spacecraft or intelligent technology, even when the data contains genuine anomalies. Yet the mere possibility exercises tremendous psychological influence on researchers and the broader public.
Once the idea enters consciousness that an object might represent a probe from elsewhere, it becomes difficult to suppress entirely. The human imagination takes over. If an interstellar object were sending a probe to survey our solar system, executing a reconnaissance mission of the sort science fiction has imagined for decades, how would it execute course corrections as it transited? It would need sophisticated systems for precise measurement of distances and velocities relative to planets and the Sun. It would need to calculate optimal intercept trajectories using celestial mechanics. It would need to apply small corrective maneuvers at strategically chosen points to adjust its course. The accelerations required for such maneuvers, given the probe's likely mass estimated in billions of tons, might be similar in magnitude to what's being observed in the data.
The timing would need to place the spacecraft in the optimal geometry for observations of multiple worlds.
And the December 19th date represents a mathematically significant convergence point, where certain observational opportunities peak and certain geometric configurations achieve their optimal values. These are the sorts of details that capture attention, precisely because they feel too coincidentally perfect to dismiss entirely. Yet they also are precisely the sorts of patterns that human minds naturally generate when searching for meaning in ambiguous data. This is the fundamental scientific challenge: distinguishing between genuine patterns and patterns that exist only in the observer's interpretation of data. Complicating the picture further is the question of electromagnetic emissions and radio signals. Multiple research teams utilizing different radio astronomy facilities have reported detecting signals in the vicinity of the object's trajectory. The frequency most frequently mentioned in these reports is approximately 1.44 GHz, which happens to correspond exactly to the hydrogen line frequency famously used in radio astronomy. This frequency holds special significance in scientific and speculative circles because it represents a mathematically universal wavelength, something that any technological civilization with radio astronomical capabilities would likely identify as significant and potentially select deliberately for communication purposes across interstellar distances. The hydrogen line frequency has been theorized extensively in the search for extraterrestrial intelligence literature.
The reasoning is straightforward. Hydrogen is the most abundant element in the universe.
Any civilization capable of radio astronomy would study hydrogen. The distinctive frequency at which neutral hydrogen emits radiation is universal, the same everywhere in the cosmos. Any technological civilization would identify this frequency as significant. Therefore, if you wanted to send a signal to another civilization, you might send it at the hydrogen line frequency as a way of saying, "We too understand fundamental physics and radio astronomy." This logic is compelling in a certain way, which is why it appears repeatedly in the scientific literature on extraterrestrial communication.
The signal reportedly exhibits characteristics described by researchers as rhythmic and almost mathematical, suggesting deliberate pattern rather than natural noise produced by non-intelligent astronomical sources. Natural astronomical signals typically exhibit randomness and irregularity, reflecting the chaotic physical processes generating them. Pulsars produce rhythmic signals, yes, but pulsars are understood to be rapidly rotating neutron stars, and their periodicity reflects the rotation of the stellar object. The reported characteristics of this signal suggest something different from known astronomical phenomena, though definitive interpretation requires much additional analysis and independent confirmation from other facilities. To be very clear, the significance of this frequency detection and these signal characteristics remain hotly debated within the astronomical community. The 1.44 GHz band experiences considerable natural radio noise from numerous astronomical sources. Jupiter produces strong emissions across multiple frequencies, as charged particles trapped in its magnetosphere spiral along magnetic field lines. The Sun itself broadcasts across effectively every frequency through various plasma heating and acceleration mechanisms. Earth's technological civilization generates enormous quantities of radio pollution across the electromagnetic spectrum, from radio broadcasts to television signals to radar transmissions to communication satellites. Isolating a discrete signal specifically at 1.44 GHz and attributing it conclusively to 3i/Atlas rather than background sources requires extremely careful analysis and validation through independent verification from other facilities.
The researchers reporting these detections have been appropriately cautious about their claims, using careful language that emphasizes the need for additional confirmatory observations and independent verification from other radio astronomy facilities. Some have emphasized that the signals could represent instrumental artifacts, background noise misinterpreted, or interference from Earth-based radio sources that happen to be present. This caution reflects appropriate scientific skepticism. Yet, simultaneously, the very existence of reports from multiple independent teams suggests something deserves investigation. Whether that something represents genuine signal from 3i Atlas or coincidental convergence of natural phenomena and instrumental limitations remains to be determined through continued observation and analysis.
Nevertheless, the convergence of multiple unusual characteristics creates a pattern that, while certainly not definitive proof of anything extraordinary, certainly justifies continued close observation and investigation. The object arrived from interstellar space on a trajectory that brought it through the solar system in a manner optimized for observation at multiple critical points. Its composition and surface properties differ from standard comet models in subtle but consistent ways that various research teams have documented. It exhibits acceleration not easily explained through conventional outgassing mechanisms without invoking increasingly exotic material properties. Electromagnetic signals appear in frequencies associated with intentional technological communication in the theoretical literature.
The timing of key observational opportunities and critical events aligns suspiciously well with windows when observational capabilities are maximized. None of these individually constitutes proof of anything extraordinary. Each could have innocent explanations grounded entirely in natural processes and instrumental limitations. But collectively, they create a puzzle that resists simple resolution through conventional physics and established cometary models alone. This is precisely the situation that science is designed to investigate and eventually clarify through systematic observation and analysis. Consider the institutional context within which this investigation proceeds. Space agencies worldwide maintain careful scrutiny of potentially hazardous objects.
Detection systems designed to protect Earth from asteroid impacts have evolved into comprehensive networks capable of identifying and tracking virtually everything larger than a few meters orbiting within the inner solar system. These systems represent the collective investment of billions of dollars and decades of technological development,
from wide-field survey telescopes and radar arrays to space-based observatories and deep space communication networks. The personnel staffing these facilities consist of highly trained professionals with access to advanced computational tools and large databases of orbital elements. Their professional reputations depend on accuracy and careful analysis. Their institutional mandates prioritize planetary protection alongside scientific discovery. Given these factors, any legitimate concern regarding a potential threat would escalate through bureaucratic channels rapidly. NASA's Planetary Defense Coordination Office would activate emergency protocols and convene internal review boards. JPL's Navigation and Ancillary Information Facility would prioritize precise orbit determination. ESA's Near-Earth Objects Coordination Center would issue technical notes. International coordination mechanisms would mobilize through the IAU Minor Planet Center and United Nations Office for Outer Space Affairs frameworks. Emergency sessions of relevant governmental bodies would convene. The phenomenon would dominate news cycles globally within hours. Instead, what we observe is relative institutional calm combined with careful, measured scientific analysis proceeding through normal channels. This pattern itself provides information.
Institutional inaction on matters the agencies take seriously typically indicates that informed analysis of all available data suggests no immediate threat requiring emergency response. Yet, the very ordinariness of the institutional response creates space for alternative interpretations to flourish in public discourse. If space agencies aren't dramatically alarmed, either the threat is genuinely negligible, or the threat is understood, but considered strategically better managed through discrete channels rather than public alarm. The first interpretation reflects conventional thinking about institutional behavior. The second requires assuming coordination among multiple agencies across different nations and institutional cultures. A coordination that would itself require explanation and evidence. The ambiguity permits both conventional and more speculative narratives to survive scrutiny simultaneously, each appealing to different psychological needs and prior beliefs. The scientific analysis proceeding now focuses on precise measurement of key physical properties that would distinguish between competing hypotheses. Spectroscopy will determine composition with high precision. Does the spectrum show the absorption and emission features expected from icy material warming near the sun? Water bands near 3 microns, carbon dioxide features near 4.3 microns, carbon monoxide near 4.7 microns? Or does it reveal signatures of exotic materials, metallic reflectance, engineered coatings, or non-thermal emission lines? The data will be deterministic. Wavelengths either match predictions or they don't. Absorption features either align with known substances or they represent something unexpected, requiring explanation and new laboratory measurements to expand spectral libraries. Astrometry represents another crucial measurement avenue. As the object continues its trajectory away from perihelion, its position relative to background stars can be measured repeatedly over weeks and months. These measurements reveal not just where the object is, but where its trajectory is carrying it. They establish whether the acceleration that was measured is continuing, fading, or fluctuating with rotation phase and solar distance. They determine whether gravitational models alone predict the observed path, or whether non-gravitational forces continue operating measurably. The measurements are geometric and mathematical. The conclusions they support follow logically from the data. Interpretation requires no subjective judgment of ambiguous signals. The object either follows predicted trajectories or it doesn't. Thermal infrared observations taken with space-based and high-altitude observatories will quantify the object's energy balance. By measuring the thermal emission spectrum, researchers can estimate surface temperatures, emissivity properties, and thermal inertia. These parameters constrain composition and texture. Low thermal inertia suggests porous, fluffy dust. High thermal inertia suggests consolidated rock or metal. If the object exhibits localized hotspots rotating in and out of view synchronized with spin, that could indicate active vents or engineered heat sources.
Thermal mapping provides an independent check on any claimed activity that might be driving non-gravitational acceleration. Polarimetry offers an additional diagnostic.
By measuring polarization of reflected sunlight across multiple phase angles, astronomers can infer particle size distributions in the coma and surface roughness properties of the nucleus. Unusual polarization phase curves, especially extreme negative polarization at small phase angles, can indicate particle shapes or compositions differing from typical cometary dust. If 3I Atlas exhibits polarization signatures far outside the solar system comet population, that strengthens the case for unusual surface properties or dust physics. Radio observations using powerful facilities will characterize any emissions the object produces or reflects. The 1.44 GHz frequency will be monitored systematically with narrowband and broadband receivers. If a signal exists, repeated observations will either confirm its reality and characterize its properties, bandwidth, modulation, duty cycle, polarization, or identify it as instrumental artifact or background noise. Multiple facilities observing simultaneously at different locations can triangulate on signal sources, determine precise frequencies after correcting for Doppler shifts, and distinguish genuine astronomical phenomena from terrestrial interference. Recording raw voltage data enables coherent dedispersion and advanced searches for structured information. If a narrowband, Doppler drifting tone consistent with an object on the measured trajectory is repeatedly detected with significant signal-to-noise by independent facilities, skepticism would justifiably yield to serious investigation. What emerges from all this analysis will provide clarity regarding what 3I Atlas actually represents. The process itself, regardless of conclusions, exemplifies science functioning at its best. Multiple independent teams gather data using diverse instruments and methods. They analyze their findings with appropriate rigor. They share intermediate results within the community for rapid cross-checks. They submit results for peer scrutiny and independent verification. Competing hypotheses are evaluated against evidence. Tentative conclusions are published, subject to confirmation or refutation through further investigation. Gradually, through iterative refinement, understanding crystallizes around what the data actually says. The questions surrounding 3I Atlas extend beyond mere identification of one object. They touch on fundamental issues about cosmic isolation and our species' place in the universe. If the object proves to be a natural comet exhibiting unusual but explicable behavior, we learn something about the diversity of cometary properties and the sophistication required to model complex outgassing physics, dust dynamics, and plasma interactions. We refine models of interstellar object formation and ejection from planetary systems. We calibrate expectations for future interstellar visitors. If it represents something more exotic, the implications cascade outward into domains far beyond astronomy: biology, philosophy, geopolitics, ethics, and the long-term trajectory of human civilization. Imagine the scenario if rigorous analysis eventually concluded that 3I Atlas possesses artificial characteristics. What follows from such a conclusion? Verification first, conducted exhaustively by multiple institutions and independent experts with transparent data release to the global community. The evidence would need to withstand intense scrutiny. But if it did, human civilization would face the reality that intelligence exists elsewhere and possesses technological capability to traverse interstellar space or to operate autonomous systems across astronomical timescales. That realization would force reconsideration of numerous fundamental assumptions underlying human philosophy, theology, and science. It would likely accelerate international coordination and space policy, planetary protection, and scientific collaboration. It might also trigger debates about messaging, response, and long-term engagement strategies. Conversely, if analysis concludes that 3I/Atlas represents entirely natural phenomena, we gain confidence in the robustness of physical models, while also learning humility about the ease with which anomalous data can mislead.
We would document precisely how unusual material properties, geometry, and solar-wind interactions can combine to mimic technological signatures. This knowledge would inoculate us against future false positives when investigating other interstellar visitors. It would refine the playbook for rapid response observation campaigns, instrument pipelines, and data sharing frameworks. Either way, the investigation serves science and understanding. The uncertainty preceding conclusive analysis creates space for imagination and speculation. Once clarity emerges from rigorous investigation, imagination gives way to established knowledge. That transition from question to answer represents the fundamental engine through which human understanding advances. We're living through one such transition point now. The coming weeks will provide observations and data that will progressively narrow the zone of possibility. The mysteries surrounding 3I Atlas will become gradually transparent as measurement and analysis accumulate, and as the global community of researchers applies collectively its best tools and judgment. For now, we remain suspended between conventional understanding and more revolutionary possibilities. The object exists. It behaves in ways that don't fit standard models perfectly. Explanations range from expanded versions of established physics to genuinely exotic possibilities. Multiple independent observation teams continue gathering data. Researchers continue analyzing and calculating.
The scientific community remains appropriately skeptical, while maintaining intellectual openness. The public increasingly follows developments with interest and speculation. The story of 3I Atlas continues unfolding before us in real time, and our responsibility is to meet it with rigor, patience, and honesty. What will eventually emerge from all this investigation? Nobody can say with certainty until the data have accumulated sufficiently to force conclusions. But the trajectory we're on suggests that answers are coming. Whether those answers confirm our deepest expectations about cosmic isolation, or force us to reconsider our place in a universe populated with intelligence and technology, the coming months will provide clarity. The universe is about to tell us something. Our task is to listen carefully, measure precisely, and let evidence lead the way. To move from speculation to understanding, it's helpful to construct clear, testable scenarios that bracket the space of possibilities. Think of these as scientific narratives that generate concrete predictions measurable with the instruments now being prepared worldwide. Each scenario explains the non-gravitational acceleration, the anomalous color, and the reported radio features in different ways. Each yields distinct observational signatures in spectroscopy, imaging, astrometry, thermal emission, polarization, and radio monitoring. The investigation's purpose over the next months is to compare these predictions with reality and eliminate scenarios that fail. Scenario A: unusual natural comet with extreme volatile composition. In this narrative, 3I/Atlas formed in a stellar system with chemistry significantly different from our own, possibly rich in supervolatile compounds like carbon monoxide, nitrogen, or exotic organics with low sublimation temperatures. As it approached the Sun, these volatiles sublimated violently, generating strong jets that produced the measured acceleration without generating a dust coma as bright as water-dominated comets typically display. The blue color arises from molecular emission bands in the ion tail, and from scattering by unusually small particles. Predictions. Spectroscopy should show strong CO and possibly N2 lines, weak water, and pronounced ion lines like CO+. The acceleration should correlate strongly with heliocentric distance and fade quickly as the object recedes. Thermal emission should indicate low thermal inertia, consistent with a fluffy, porous surface. Polarimetry should show signatures of small particle-dominated dust. Radio signals should not repeat coherently after rigorous RFI mitigation. Scenario B: CO2-dominated comet with microjet geometry and rapid rotation. Here,
Typical volatiles exist, but outgassing is geometrically concentrated into microjets along fractures and pits, producing significant anisotropic thrust with minimal total mass loss. Rapid nucleus rotation sweeps these jets, producing quasi-periodic acceleration components. The blue color emerges from fluorescence of CO2 and CO under intense solar UV. Predictions. Time-resolved astrometry reveals periodic acceleration modulation matching rotation period. High-speed photometry shows rotational light curve with amplitude variations from jet-driven activity. Spectroscopy reveals strong CO2 and CO bands. High-resolution thermal imaging detects hot microregions consistent with jet vents. Polarimetry trends align with compact, fresher grains. Scenario C. Electromagnetic interaction with solar wind and interplanetary magnetic field. In this case, the object becomes sufficiently ionized near perihelion that coupling to the solar wind and magnetic field imposes Lorentz forces on an extended plasma environment anchored to the nucleus, imparting effective acceleration without massive mass loss. The blue color arises from forbidden line emissions in the plasma. Predictions. In situ solar wind data and heliospheric models correlate transient magnetic sector structures with measured non-gravitational accelerations. Remote sensing reveals aligned plasma structures consistent with magnetic draping. Spectroscopy shows strong ion emission lines and line ratios indicating low-density plasma excitation. Astrometric deviations correlate with solar wind parameters measured by spacecraft. Scenario D. Fragmented nucleus with sublimating debris cloud. The object underwent partial fragmentation near perihelion, releasing a swarm of centimeter to meter scale fragments producing collective outgassing thrust while dispersing enough light to appear blue due to Rayleigh-like scattering. Predictions. High-resolution imaging resolves secondary condensations in the coma with measurable relative motions. Photometry shows stochastic brightness fluctuations from fragment mutual occultations and jet flickering. Spectroscopy shows mixed volatiles with episodic enhancements. Astrometry reveals step-like changes in trajectory during fragmentation events rather than smooth acceleration. Scenario E. Artificial object with active propulsion. In this most extraordinary scenario, the acceleration reflects deliberate maneuvers executed by onboard systems. The blue color could arise from ion thruster plumes dominated by xenon or other propellants, or from engineered surfaces with specific reflectance properties. The radio signals represent telemetry or beacon transmissions. Predictions. Acceleration vectors align with optimal transfer geometry rather than solar-driven sublimation patterns. Thrust persists even as heliocentric distance increases beyond regimes of significant sublimation. Narrowband, Doppler drifting radio tones repeat with modulation patterns inconsistent with known natural sources. High-resolution imaging resolves geometric edges or symmetry inconsistent with natural nuclei. Thermal maps reveal localized, persistent hotspots with engineered duty cycles. Scenario F. Ancient autonomous probe exhibiting stimulus-responsive activation. A conservative variant of E, this scenario posits a long-dormant artifact that activates specific functions when solar flux exceeds thresholds near perihelion, producing transient blue emission and short-lived thrust. Predictions. Activity spikes only near flux thresholds with hysteresis. Long periods of quiescence follow. Radio emissions appear as brief, structured bursts, temporally linked to activation, not continuous carriers. Post-perihelion acceleration decays faster than sublimation models predict. These scenarios are not mutually exhaustive, but they span the primary explanatory classes: unusual chemistry, geometry/rotation, plasma physics, fragmentation dynamics, and artificiality. The value of articulating them explicitly lies in their predictive power. Each provides clear observational tests. Over the next observation windows, teams can intentionally seek discriminants: periodic versus aperiodic acceleration, volatile ratios in spectra, correlation with solar wind parameters, presence or absence of fragments, persistence of thrust with increasing solar distance, properties of any radio emissions, morphological structure at the highest achievable resolution. Now consider the observation plan most likely to yield decisive evidence. International coordination will be essential. Ground-based optical/IR spectroscopy using 8 to 10 meter class telescopes, VLT, Keck, Subaru, Gemini, should target volatile bands from near IR through mid-IR, scheduling dense cadence around twilight when geometry permits. JWST, if constraints allow, can probe faint molecular lines and thermal emission with unparalleled sensitivity, though bright object and moving target constraints must be navigated carefully. Hubble can contribute UV spectroscopy to capture ion lines inaccessible from the ground. Wide-field survey telescopes like Pan-STARRS and ZTF should provide high-cadence photometry to capture rotational light curves and activity spikes. Astrometry demands a network approach, many modest telescopes contributing frequent, precise positions to reduce statistical uncertainties and resolve periodic signatures tied to rotation or jet precession. Polarimetry campaigns, while niche, can be decisive. Coordinated observations across phase angles can map the polarization phase curve in a way impossible with ad hoc measurements. On the radio side, facilities like Greenbank Telescope, Meerkat, FAST, and the VLA should conduct synchronized campaigns with standardized RFI excision, drift rate searching, and raw voltage capture, enabling reprocessing with evolving algorithms. Observations near the hydrogen line are tempting, but broader frequency coverage reduces confirmation bias and increases discovery space. Complementary heliophysics data must be integrated. Solar wind speed, density, and magnetic field vector from spacecraft like Discover, ACE, Solar Orbiter, and Parker Solar Probe inform tests of Scenario C. Modeling groups can assimilate these data into global heliospheric models to predict plasma draping and force coupling magnitudes, which can be compared directly against residuals in astrometric solutions after gravitational forces are removed. Public communication presents a parallel challenge. The appetite for dramatic conclusions will grow as data accumulate. The role of responsible science communicators is to frame uncertainty correctly, to explain why multiple hypotheses remain viable, to share what would count as decisive evidence, and to demonstrate how the process of elimination proceeds. Overpromising risks disillusionment. Overcaution risks missed educational opportunities. The right tone is measured curiosity anchored in method. Finally, it is worth articulating the ethical dimension should evidence for artificiality strengthen. A non-contact posture that prioritizes observation over transmission aligns with widely discussed messaging to extraterrestrials guidelines. It preserves safety while maximizing learning. Any decision to transmit intentional signals in response to potential probes would require international deliberation, far beyond any single nation's mandate. In the near term, the only ethically clear action is to observe carefully, share data openly among qualified researchers, and avoid unilateral steps that could foreclose global consensus. The next months will either pare this branching tree of scenarios down to one or two, or reveal that the phenomenon is richer than any single narrative captures. Either outcome advances knowledge. The practical work now is simple in concept and demanding in execution. Measure better, more often, across more wavelengths with tighter coordination. Let the universe show its hand. And be ready to recognize what it reveals, whether it is the surprising ingenuity of natural physics or the unmistakable signature of minds not our own. To understand how a natural body might generate thrust sufficient to produce the measured accelerations without evaporating into obvious coma brightness, consider the microphysics of cometary jets. Sublimation rarely occurs uniformly across a comet's surface. Instead, volatiles are exposed through fractures, pits, and collapsed caverns.
Sunlight penetrates porous regolith, heats subsurface pockets, and drives gas flows along tortuous channels. When these channels vent to space, the outflow expands supersonically, entraining small dust grains and forming jets. The thrust from any single microjet is tiny, but the vector sum across hundreds or thousands of vents can become dynamically significant, especially if the surface distribution is asymmetric or if rotation modulates exposure cyclically. Rotation plays a central role. Imagine a nucleus spinning with a period of hours.
As the sun rises over a vent field, sublimation spikes, generating thrust oriented partly radial and partly tangential relative to the surface. As the field rotates into shadow, activity wanes. If vent fields cluster preferentially on one hemisphere because of past thermal processing or exposure history, the time average thrust in inertial space does not cancel perfectly over a rotation. A net acceleration persists. The magnitude depends on jet mass flux, outflow velocity, lever arm geometry, and duty cycle tied to the rotation period. High-cadence astrometry can, in principle, detect periodic modulation in a long-track and cross-track residuals synced to rotation, an observational signature that strongly favors jet-driven acceleration over other scenarios. Thermal inertia and conductivity modulate the phase lag between insolation and sublimation. Low thermal inertia surfaces respond quickly. Peak gas flux occurs near local noon. Higher thermal inertia shifts the peak into the afternoon sector. This matters because the direction of thrust relative to the Sun-comet line rotates with the local hour angle of peak flux, thereby changing the vector components that feed orbital energy and alter the trajectory. A midday peak drives thrust roughly anti-solar, pushing the object outward. An afternoon peak adds a tangential component that can speed or slow orbital motion. Observers can exploit this by correlating the sign of measured non-gravitational parameters with modeled thermal lags derived from multiband thermal IR data. Dust dynamics adds another layer. The size distribution of expelled grains controls coma brightness and color. Submicron grains scatter blue light more efficiently than red, producing a bluer optical signature even when the bulk material remains compositionally ordinary. If 3I Atlas sheds primarily small grains because the gas velocity is high and cohesive forces on the surface favor detachment of the smallest particles, the coma could look spectrally blue without requiring exotic chemistry. Polarimetric phase curves sensitive to grain size can test this. Small grain comae produce distinctive negative polarization at small phase angles and a steeper polarization slope with phase. Now consider the plasma environment. As gas escapes and becomes ionized by solar UV, it forms an ion tail interacting with the solar wind. Magnetic draping occurs when the interplanetary magnetic field bends around the obstacle presented by the expanding plasma cloud. Under certain orientations and solar wind conditions, the Lorentz forces acting on the charged environment can, through complex coupling, transfer small net momentum to the nucleus. Typically, this force is negligible, but during strong solar wind compressions or sector boundary crossings, transient effects could briefly enhance coupling. If 3I Atlas's peak anomalies coincided with such heliospheric events, we might see correlated deviations in the astrometry. Cross-discipline analysis between heliophysics and comet dynamics thus becomes crucial. Fragmentation physics can also masquerade as steady acceleration. When a nucleus sheds centimeter to decimeter pieces that continue to sublimate, the system's center of mass can shift relative to the brightest condensation that tracking software uses for centroiding. This produces spurious astrometric trends that reduction pipelines might interpret as non-gravitational acceleration. High-resolution imaging that resolves secondary condensations eliminates this ambiguity. If fragments exist, their differential motion relative to the primary condensation should be detectable and modelable, and the astrometric solution can be corrected to reflect true center of mass motion. Let's return to the artificiality scenarios, not to sensationalize, but to define falsifiable markers. Ion propulsion plumes have characteristic spectral fingerprints. Xenon, used in human-built ion thrusters, exhibits optical and near-UV emission lines. However, Visibility at interplanetary distances is dubious unless plume densities are far higher than human designs produce.
More promising are narrowband radio emissions. Engineered systems often use coherent, narrow spectral lines to concentrate power. A repeated narrowband signal with Doppler drift consistent with a moving transmitter and exhibiting non-natural modulation patterns would be hard to reconcile with known astrophysical sources. The bar for acceptance remains high. Repetition across instruments, geolocation rejection of terrestrial interference, consistency with trajectory, and information-bearing structure that survives statistical randomness tests. Geometry offers another discriminator. Natural nuclei tend toward irregular shapes sculpted by erosion and fragmentation. While some geometric edges can occur naturally, persistent planar facets or repeating angles resolved at stable orientations across rotation cycles would be unusual. Light curve inversion techniques, reconstructing shape models from changes in brightness as the object rotates, could reveal whether the nucleus fits typical comet-like irregularity or exhibits symmetry difficult to explain through erosive processes. If radar becomes feasible at sufficient signal strength, delay Doppler imaging could add powerful constraints on shape and surface texture. What about long-term behavior? If the non-gravitational acceleration persists months after perihelion with only mild decline despite decreasing solar flux, that weakens jet-driven models and strengthens scenarios involving internal energy sources or propulsion. Conversely, a steep decay proportional to an inverse power of heliocentric distance supports sublimation control. The community should therefore commit to an extended monitoring campaign through spring, not just a December sprint.
Many mysteries dissolve only under the pressure of time series data.
Public understanding benefits when narratives emphasize process over spectacle. The gripping part of this story is not merely whether 3i Atlas is natural or artificial, but how science adjudicates between complex, competing explanations under uncertainty. Showing the work, the calibrations, the error bars, the cross-checks between instruments, the null results alongside positive detections, builds trust and inoculates against future misinformation. Viewers should see scientists changing their minds when evidence warrants. That's not inconsistency. That is the point of the method. As we close this expanded section, it's worth imagining two equally profound but different outcomes. In the first, 3i Atlas yields a masterclass in cometary physics. Microjet thrusts, rotation-modulated acceleration, exotic but natural volatiles, and a plasma interaction case study integrating heliophysics with small body dynamics. In the second, even after exhaustive natural explanations are modeled and tested, residual signals persist. Narrowband radio tones repeat with structured modulation. Thrust vectors misalign with solar heating. Thermal maps show periodic hotspots decoupled from insolation. If such evidence survives scrutiny, the conversation necessarily shifts. Either outcome enriches human knowledge. Either path is worth walking with care. The cosmos rarely hands us certainty quickly. It rewards persistence, the accumulation of measurements, the humility to be wrong, the courage to ask uncomfortable questions, and the discipline to let answers arrive on their own schedule.
3i/Atlas is not a riddle to solve in a headline.
It is an experiment in how a civilization learns. A disciplined way to converge on truth is to treat this as a probabilistic inference problem. Begin with prior beliefs about interstellar objects based on the small but informative sample we have, Oumuamua and Borisov, augmented by the vast population of solar system comets. Priors strongly favor natural explanations, unusual chemistry, geometry, rotation, fragmentation, plasma coupling. Artificiality begins as a vanishingly small prior because it has never been confirmed observationally. The role of new data is to update these priors. When data arrive that standard models predict with high likelihood,
the posterior probability of natural scenarios grows.
When data persistently fall in regions of parameter space that standard models assign low likelihood, the posterior weight shifts toward alternatives. What data shift weight meaningfully? Independent confirmation of a persistent, directionally coherent, non-gravitational acceleration that does not track heliocentric distance and thermal models would strongly penalize sublimation-driven thrust. A narrowband radio signal repeating overnights, recorded by multiple geographically separated facilities, with Doppler drift matching the object's trajectory and showing non-random modulation, would dramatically shift weight toward technology. Conversely, detection of strong CO and CO2 bands with line ratios matching outgassing models, periodic astrometric modulation at the rotation period, and rapid post-perihelion decay of thrust would push weight decisively back to natural scenarios. To operationalize this, research teams can define likelihood models for each scenario outlined earlier. For scenario A, the likelihood of observing a given volatile ratio, polarization curve, and thermal inertia can be computed from known distributions of comet properties extended with priors for interstellar chemistry. For scenario B, the likelihood of a particular rotation period, thrust vector pattern, and light curve amplitude can be simulated using jet geometry ensembles. For scenario C, coupling strengths can be predicted from measured solar wind conditions using MHD models. For scenario D, the probability of fragment detection given instrument limits can be calculated. For scenarios E and F, likelihoods remain necessarily broad, but can be bounded by energetics and signal detectability. Integrating evidence across instruments requires careful handling of systematics. Astrometric residuals can be contaminated by centroid shifts when comi are asymmetric. Spectral features can be misidentified under poor sky subtraction. Radio facilities face relentless terrestrial interference. Only coincident detections with consistent drift and polarization should be considered strong. Thermal IR can be biased by background subtraction near the ecliptic. Polarimetry is notoriously sensitive to calibration. A rigorous approach shares raw data and reduction code openly, so the community can replicate analyses and test sensitivity to assumptions. The calendar matters. The December window is the inflection point for optical IR spectroscopy and high-cadence astrometry once solar elongation improves. The weeks that follow, as solar distance increases, are crucial for testing decay laws of any measured acceleration. Radio monitoring should bracket December with pre- and post-window campaigns to search for activity-linked emissions. Heliophysics coordination should be continuous to correlate any dynamical anomalies with sector boundaries, CMEs, and high-speed streams. Now step back and consider the human dimension. Why does this object capture imagination so powerfully? Because it sits at the boundary where the unknown brushes against our desire for company in the cosmos. It reminds us that our instruments have become keen enough to register whispers, a faint acceleration here, a spectral tilt there, a possible tone near a frequency theorists have long suggested as a beacon. It forces a culture saturated with instant takes to endure a slower tempo, the tempo of careful measurement, because reality does not rush to accommodate our timelines. This is also a story about humility. If 3i/Atlas turns out to be natural, as priors suggest, we will still have learned a remarkable amount about interstellar debris and the diversity of planetary system byproducts. We will have sharpened the world's observational reflexes for the next visitor. And there will be a next visitor. If it turns out to be artificial, the scale of humility required expands incomprehensibly, and our work will have only begun. To listen, to understand, to decide how to respond as one species rather than many. Either way, there is value in readiness. Readiness looks like well-calibrated instruments, transparent data practices, international collaboration, and a public educated to appreciate how knowledge grows.
It looks like refusing to sensationalize while also refusing to look away. It looks like steady attention. As we approach the next visibility window, hold two thoughts at once.
First, extraordinary claims require extraordinary evidence, and we do not have that evidence yet.
Second, the universe sometimes surprises those who are prepared to notice. We have given ourselves the gift of instruments that can notice. Now we give ourselves the discipline to wait, to measure, and to let the sky speak in its own language and on its own schedule. What comes next is simple. Watch, record, compare, and update. The rest, interpretation, meaning, consequence, will follow the evidence. Until then, let curiosity be patient, and let patience be curious. If this investigation is to become a template for how we meet the unknown, it needs not just instruments and models, but governance, clear norms about who decides, who speaks, and how evidence moves from lab benches to public understanding.
Consider three pillars that can make the difference between confusion and clarity: transparency, coordination, and restraint. Transparency means pre-registering analysis plans when feasible, publishing calibration files, and releasing raw data alongside reduced products with thorough documentation. It means acknowledging uncertainties explicitly: instrumental noise floors, sky subtraction residuals, centroiding biases in crowded fields, and assumptions in thermal models. It means sharing negative results, like non-detections of radio tones during quiet solar wind conditions, so the literature does not tilt toward apparent positives. In practice, this looks like a public repository where spectroscopic extractions, wavelength solutions, and error spectra live, like astrometric residuals plotted against rotation phase, like radio waterfall plots with RFI masks and drift rate searches available for reanalysis. Coordination means aligning observing windows across longitudes and hemispheres to span diurnal gaps, exchanging quick-look reductions so teams can pivot to interesting behavior within hours, and ensuring that heliophysics monitors stand ready to contextualize any dynamical anomalies. It means a shared cadence: nightly photometry for rotation and outbursts, weekly deep spectra for volatile ratios, continuous radio blocks spread across facilities to defeat local interference, scheduled polarimetry around key phase angles, and routine ingestion of solar wind parameters into prediction dashboards that tell observers when plasma coupling tests are most favorable. Restraint is the ethic of not outrunning the data. It is resisting the gravitational pull of premature certainty. It is choosing language that leaves room to move when evidence changes, consistent with, suggestive of, requires further observation. Restraint does not dampen curiosity. It protects it. It keeps doors open. In moments when cultural appetite for definitive answers peaks, restraint is the scientist's way of honoring the future capacity to be surprised.
With norms in place, turn to the human implications of each endgame. If the weight of evidence cements a natural origin, the teaching moments multiply. A video like this one can become a guided tour through modern inference: how small forces integrated over time reshape orbits, how spectroscopy reads chemistry at astronomical distances, how plasma physics ties the sun to small bodies. It becomes an invitation to the next generation to build better instruments, smarter pipelines, and more adaptive observing networks. It shows that good questions sometimes end in the confirmation of what nature already knew, and that this, too, is a win. If evidence accumulates in the opposite direction, if, despite conservative priors, the best explanation involves technology, the social work begins in earnest. The first responsibility is verification to the point of boredom. Independent labs, different pipeline stacks, public data challenges, hostile reviewers. The second is governance. International bodies convene to determine posture, messaging, and safety protocols, drawing on decades of SETI deliberation. The third is culture. Narratives that help billions integrate a new cosmic fact without panic or nihilism. This is where the humanities stand shoulder to shoulder with physics. We will need philosophers to refine questions, artists to make meaning, historians to remind us how civilizations metabolize shock, and communities of faith to locate continuity in a wider cosmos. Between those poles lives a spectrum of middle outcomes: partial artificiality signals that remain ambiguous, volatile chemistry that is unique but natural, radio features that look structured until better RFI excision flattens them, thrust profiles that flirt with anomaly before decaying with the square of distance. These middling conclusions are not failures. They are the truth most often delivered by the world: textured, provisional, resistant to slogans. So, what does the next practical week look like for an observer or a curious viewer? Night 1. Acquire time series photometry and submit to the community cadence server. Check the evolving rotational period estimate and watch for outburst flags. Night 2. A spectroscopic run aimed at CO and CO2 bands. Upload extracted spectra with error bars and calibration frames.
Day 3. Run the astrometric solver with coma-aware centroiding. Publish residuals relative to the current ephemeris.
Day 4. Radio time. Observe wide and narrow bands. Capture raw voltages for 2 minutes every scan. Day 5. Polarimetry at the predicted optimal phase angle. Share Stokes parameters with uncertainties. Day 6. Integrate solar wind conditions into a joint forecast for dynamical tests. Day 7. Synthesize. Did rotation-linked modulation appear? Did volatile ratios evolve? Did thrust parameters change with heliocentric distance? Did any radio lines repeat with consistent drift? For storytellers and educators building content around this effort, the structure nearly writes itself. Open with the small force that matters over time, the intuition breaker that says, this should be negligible, and yet. Move into the visible, the blue tilt, the faint tail, the jet flicker.
Drop to the invisible, the ions, the fields, the wind.
Pan out to the network, domes under cold skies, dishes turning in concert, the quiet heroism of calibration. Return to the fork in the road, nature's ingenuity or someone else's. Close with a promise tethered to a date, not as prophecy, but as a waypoint, when the sky will either deepen the riddle or begin to speak plainly. Perhaps the most honest closing is an invitation. Not believe and not dismiss, but join. Join the slow listening that science demands. Join the practice of changing one's mind when reasons change. Join the willingness to share credit and blame with strangers across borders who are, for this brief window, colleagues in wonder. The cosmos has given us a moving question mark. Our answer is not to shout an exclamation point back at it. Our answer is to measure, to think, and to stay. When the next observation window opens, we will be there. Eyes and instruments ready, models sharpened, expectations softened. Whether 3I/Atlas is a lesson in the subtlety of comets, or a letter from the dark addressed to a species finally able to read it, we will treat it the same way, with care.